Hello, everybody. My name is Longxi. I'm talking about the interpretable and deployable segmentation and enhancement models for pulmonary tissues. I will first give background. COVID-19 will cause primary parenchyma lesions during hospitalization, and after discharge, most of the survivors' computed tomography will back to normal. However, our follow-up Concord and recent researches found most of the survivors have decreases in their non-functions. For example, like this patient, he has suffered from severe sequela, but his CT looks quite normal. Thus, we come up our research aim. We want to enhance the parenchyma by dozens of times to see whether they are subvisual COVID-19 lesions. We usually observing the CT under the non-window. However, the non-window is not good. The window width for non-window is too large that some of the lesion signals may be overwhelmed and unnoticeable. Thus, we want to enhance the parenchyma by removing irrelevant tissues and calculate the scan-specific optimal windows, which only focus on very small amount of CT signals. This is our final findings. The original CT looks like this, and after enhanced, we get some subvisual lesions, and we quantify these subvisual lesions and analyze its correlation with some key respiratory sequela. And we found most of the COVID-19 survivors have some subvisual lesions, and these lesions can explain key respiratory COVID-19 sequela. And let's see how we do the enhancement. The enhancement has 3 steps. First, we should segment out some pulmonary tissues like lungs, airways, blood vessels, and then we remove irrelevant tissues based on these segmentations and only leave the parenchyma that looks normal under the non-window. And finally, we calculate the optimal windows for observing the parenchyma based on the parenchyma CT signals. And then we quantify the local CT lesions. We first generate parenchyma enhanced images for COVID-19 survivors, as well as healthy people as control. And then radiologists will give ground truth for these novel lesions like this. And we then develop segmentation models based on these annotations. And you see the segmentation here is a 3D problem. And we try to use a 2.5D approach plus interpretable loss. The 2.5D approach merges 3 2D units from different views. And we developed the loss based on our prior knowledge about different tissues. And our segmentation model is light, fast, robust, and reached human comparable performances. The model architecture is simple. It is 3 2D units segmentation from 3 different views, and then we combine 3 segmentation probability maps and get the final segmentation. And we calculate the interpretable loss based on different tissue property. For example, the airway has strong self-similarity, which means there should be same amount of information for each branch level. Thus, we can calculate the information density map, which gives the optimal penalty for each pixel. Thus, we can get a very good loss function. And based on this loss function, we dramatically increase the dice for tiny structures. Like for tiny airways, we improve the dice from 0.52 to 0.78. And the 2.5D approach has other advantages because during training, the model do not know the 3D structure. Thus, if it output reasonable 3D segmentation, which means we should have a good performance, like the rib contours, the tree-like structures. And we also find our model is robust and human comparable. On the left, it's the segmentation from third party. It's the data from Saudi, and our training set is in China. And you see it's look natural. And the ground truth only have maybe 5 branches, but we may have 7 to 9 branches. It may human comparable. And as conclusion, we use 3.5D structure and interpretable loss to have a good segmentation performance. And our segmentation structure is fast, light, and robust, which is suitable for deployment. And our pulmonary parenchyma enhancement tool can also be a good way for analyzing novel parenchyma lesions. Thank you very much.